Hello. Today I'm going to show you how to do this integral in a specific method. I'm going to try and do it, quite quickly. I'm going to still try and explain everything, but no one wants to watch some 1 million year long video, so let's get straight into it. So we're going to start off by, I should probably say what the integral is. It's the integral from minus infinity to infinity of e to the minus x squared dx. Alright, so we're going to start off by squaring this integral, and notice that when you square it, the actual variable is arbitrary, so when we times it by itself, so this is the first one in the square, when we times it by itself we're going to choose a different variable, namely y. Why do we choose y? Why not? That's kind of cringe. Alright. After we've done this, we're gonna basically rearrange this to form a double integral. The first with respect to x, and the second, I guess, with respect to y. Not sure that it matters. Maybe it does, huh? No, they're literally the same integral. Comma. Alright. And the integrand is going to be e to the minus x squared times e to the minus y squared, which is e to the minus x squared plus y squared. And this, when we see this, this is like the equation of a circle. We're gonna now look to transform this integral into polar coordinates. That's what we'll do. So, firstly, we're going to consider the domain of the integral. So, in Cartesian form, the domain is just the whole xy plane, right? It's from minus infinity to infinity on both coordinates. So, it is the entire xy plane. How are we going to sort of transfer this to polar coordinates is kind of simple. Let's say this is a point r theta, and we want to cover the entire plane, so r is going to have to go like in infinite length. So r, I'll write it down here, r is going to have to go between 0 to the origin and infinity, and theta, well, it just has to cover the sort of 362 pi radians. We use radians for polar coordinates, so theta has to go between these. So this is like the equivalent of these limits in polar coordinates. And then we also have to deal with the actual function. I didn't close that bracket. The actual function, and then also the dx and the dy, sort of volume element. So I'm not going to explain this too much, but dx dy in a multi-dimensional integral we usually say is dA. I'm not going to explain this, so I want to keep the video short as possible. But to transfer this to polar, we call it dA prime, and that is equal to r dr d theta. So basically we have to replace the dx dy with r dr d theta, and then we have to actually change the function lastly. So we have so if we want to put this in polar coordinates, x is r cos theta squared plus r sin theta squared, and obviously cos squared plus sine squared is 1, so this just simplifies to this. So I think we're ready to basically transform the integral to polar entirely. I ran out of space, so I have another pane here, so let's do that. So let's do the across the theta, so part of the integral first. That runs through these limits, and it's with respect to theta. And then the second part runs through 0 to infinity is the r dr, and then we have our function, which is this. Actually, let me write this differently. Okay, so now we can get started with integrating the first part of the integral, and then the second part of the integral. First, second. Okay, so now we can see that this has like, now that we've transferred it to polar, the actual function has like a pretty clear antiderivative. So let's do this in red, sure. This, oh, that's really bad. This, oh wait, I just realized this is equal to d of dr of, what's the antiderivative of this? It doesn't take long to figure out that it is minus e to the minus r squared over 2. Alright, so they're equivalent, so we're just going to sub this in. dr. Actually, this minus half here, we can actually just factor that out to the front of the integral. Just leave this. And then, by the fundamental theory of calculus, if you integrate a derivative, you're just going to get that function back. So we're left with just this function evaluated at the limits, which are 0 and infinity. Okay, when you plug in 0 into this, you get 1. When you plug in infinity, you get 0. So it's going to leave you with a 0 minus a 1, which just equals minus 1. And then you can see that the final integral, you can take the minus 1 out as well, so we're just going to get half the integral from 0 to 2 pi d theta, which is clearly just half of theta valued at these, which is just half of 2 pi These cancel out, and then we're just left with pi. Alright, let's go back to the start and wrap this up. So we just figured out that I squared equals pi. So if we just square root everything, it's a big square root, we get that I equals square root of pi. So yeah, the square root of pi. Thanks for watching.